And we'll go over some more of these problems that we were going over last time. I believe we already covered page 142, but we have not covered page 145 yet. The problems I'm looking at for the handout that I gave you guys. Let me share the screen with you and go to that page. All right. No. Well, I guess this is actually 4. Let's go back to 5.4. Okay. I think I'm going to find it here. There we go. There's 5.22. All right. Can you see it okay on your screen?
Yes.
All right, so this is a table where we see relative frequencies. It says here a survey of employees at a large company found the following relative frequencies for the one-way distances they had to travel to work. They had to travel to arrive at work. Okay. So let's just review the categories here. It's less than 5 miles, 6 to 10 miles, 11 to 15 miles, 16 to 20 miles, 21 to 30 miles, and anything greater than or equal to 31 miles. I'm assuming the mileage is rounded to the nearest whole number. All right, so what is the probability that a randomly selected individual will have to travel 11 or more miles?
Uh, 0.37.
Correct. And did you add the 4 numbers here?
Yes.
Right, 11 to 15, 16 to 20, 21 to 30, and greater than or equal to 31. So you added the 4 relative frequencies. So we're going to use the relative frequencies as a substitute for probabilities, right? The relative frequency approach, right? Yeah.
Right.
And one other way of doing this, it wouldn't have made much of a difference. There's not much. There's only 6 categories here, but you could have said 1 minus the sum of the first 2, right? 1 minus.
Oh, right. Yeah. Yeah.
1 minus 0.63 would have been 3.37. Both ways, of course, work. B, what is the probability that a randomly selected individual will have to travel between 6 and 15 miles? Lon, what do you think? Between 6 and 15 miles?
141.
Right. The sum of these 2 categories, B and C. That's right. At a 0.25, 0.16 gives you 0.41. All right. Now, in the handout I gave you, I did show a Venn diagram for this, right? Draw a Venn diagram that includes the relative frequency probabilities in the table. What you would show, obviously, is you could show 5 of the 6 being inside little boxes inside the big box, the Venn diagram box. And then the 6th one would be the one outside of those 5 boxes. Well, that's one way of doing it. And do the boxes inside, do they intersect at all? With these categories, are they mutually exclusive categories? Do they intersect at all? No. So those boxes would be separate from each other. You know, like inside the Venn diagram box, you have these little boxes for each of the, let's say the first 5, and then outside of those boxes, you would put F for the last one, maybe, right? There's, different ways of doing it, but the little boxes inside the big box would not intersect because they're mutually exclusive. Using the letter identifications provided, calculate the following probabilities. What's the probability of A or B or E? A or B
0.7.
or E. What was that?
0.7.
0.7, that's right. These are mutually exclusive. So the addition rule for a mutually exclusive means you just add the probabilities. So A or B is adding those up as 0.63, and then E adding 0.07 to that is 0.7, right? How about A or F?
0.43.
Right, just simply adding those probabilities. How about not A or B?
6.62.
Correct. Now in this case, these aren't mutually exclusive, are they?
No.
Yeah, not A includes B. So not A would actually have B inside it. So simply not A would be 1 minus 0.38. All right, so we're good so far, right? And then the last one would be A or B and not C. I think that's a not C there. Is that a not C? Let me see. Hold on. I get my face really close. Yeah, it looks like it's not C. So it's A or B or not C. The actual book is clearer. Yeah, go ahead.
0.84.
So it's A or B.
Oh, A or B. Okay, sorry. No, so A or B or not C. Wouldn't that be 0.84? Because you're basically only excluding C there.
That's correct. That's right. 1 minus 1.16 is 0.84. Yeah, you're only excluding C. A or B would just be the sum of these two. Not C would be these two plus D, E, and F. Yeah, so it's basically the sum of all the 5 other than C. All right, good. So I think you're all getting it pretty easily. Let's go to page 150. Let's go to the next one. 150 is, now we'll deal with the multiplication rules. And we're going to look at I'm not sure. I didn't write down the problem number here, so I have to see which one I'm looking at here. All right, hold on 1 second. I have to see on page 150 problem. No, they didn't actually write the problem. Oh, just give me a second here and see which one. One with homeowners and rents. And dishwashers, right? Yeah. So it's actually 33. 5.33. So hold on a second. So let me read it to you. It's been reported that 57% of US households that rent do not have a dishwasher, while only 28% of homeowner households do not have a dishwasher. If one household is randomly selected from each ownership category, determine the probability that, and then you have these 4 different problems here. So the first one says that neither household will have a dishwasher.
Let me get my calculator.
And you can leave your answers to 4 decimal places. So while you're doing that, I'm going to, don't look at the answers, the ones I gave you. Try it on your own. And what I'll do is I'll open up I'll give you a couple minutes to work on that one, and then we'll do the rest of them. Just one comment, when you have a problem like this, it's very important to define your variables, right? Find, in this case, it would be the variables representing the different events. And then write down the probabilities that are given based on the language that's in the problem. All right, do you have an answer for this one? It looks like you've stopped. Yes. An, do you have an answer? I think Stephen. Yeah. What is your answer?
0.1596.
Correct. Okay. And you didn't look at the answers I posted?
No.
All right. All right. So let's look at the and Stephen, you got the same thing?
Yeah.
Okay. So let's just take a look at how I set it up. So I set up these letters for the events just so that they make sense. H means person's a homeowner. H not means they're a renter. Okay, that's what I used. D means they have a dishwasher. D, not D means they don't have a dishwasher. So the first, what was given in the problem is the following. It says, 50% of US households that rent. All right. 50% of US households that rent do not have a dishwasher. So if we're using that relative frequency as an estimated probability, this is a this is the probability that the person does not have a dishwasher, given that they rent. This is a conditional probability that they're giving here. Han, did you write that down also?
Mm-hmm.
Conditional, yeah. And then the other one was that 28% of homeowner households do not have a dishwasher. So that's this one here, 0.28. Now, conditional probabilities, this is something you should know. Maybe you already figured it out. Conditional probabilities have the same rules as unconditional probabilities in terms of being between 0 and 1. This condition, for example, this conditional probability that the person is does not have a dishwasher, given that they rent, the complement of that must be that they do have a dishwasher, given that they rent. The sum of these two must be equal to 1, right? So the condition stays the same. It's just the probability itself, D or not D, adds up to 1. Same thing over here for the homeowners. Hold on a minute. Now, same thing with the homeowners. This is the probability of not having dishwasher, given that you're a homeowner, and this is the probability that you do have a dishwasher, that you're a homeowner. These two probabilities have to add up to 1. So what you simply did was you multiply these two probabilities to get your answer, right? For A. Why is it that you did not use? Why do you say that you simply multiply them? What's your reasoning for that?
Well, they're considered independent events. I think that would be the term.
Independent, right? They're independent from one another. Okay. So we're assuming that, right? That the householders, that the householders and the renters don't affect each other, right? There's no, okay. All right. Now, don't look at the answers that I wrote down here. I'm going to stop sharing here. Let's go back. Let's do the second one. Both households will have a dishwasher. That's part B. And why don't you actually work on part B, C, and D? You have the books in front of you? Do I have to read it to you?
No, I actually did them already.
You've already done them. Okay. How about you, Han?
Yeah, I did. I finished already. Yeah.
Okay. Would you like to teach the class?
Hey, you know what?
I could do something else.
I didn't put the notation down that you did, so I could do that.
All right. Okay. All right. So it's the same thing for B, except where it's the probability of D given not H times the probability of D given H, right? People who do own a dishwasher. And then C is the renter household will have a dishwasher, but the homeowner household will not. So we multiply the 0.43 times the 0.28 to get 0.1204 for C. And the last one, the homeowner household will have a dishwasher, but the renter household will not. And that one we're multiplying 0.72 times 0.57 to get 0.4104. All right, so both of you seem to be fine with that. I think most students who are new to this course would probably struggle with this problem totally, you know, because they wouldn't know how to set up the conditional probabilities that were given in the problem. They probably would just say, when they say 50% of US households that rent do not have a dishwasher, they might even consider that to be a joint probability, right? They would say the probability of D and H, or excuse me, the probability of not D and not H. But it's not that. Because the probability of not D and not H assumes that you're selecting from the whole population, not just the population who rents. Okay? But again, many students would struggle with this, but you guys are my brilliant students, so it makes my life easy. I'm not used to that, actually. It's nice to have students who get things the first time. All right, now we already went over the Bayes theorem one, right? We already went over that. But we could try, if you want, just for the fun of it, 5.45. And that is on, that's on page 155. Okay, so what I'm going to do is go back and find that problem. And what I actually will do 5.45, 5.46. We already did the other one, right, in class, the one with the machines. But I want you to try this one to show you the difference in complexity sometimes in these Bayes theorem problems. So go ahead and try that one, 5.45, and then if you think it's easy, try 5.46 and see if you get the answers.
Okay, I got an answer, but I'm not sure if it's right.
Yeah, just a little more, this is a little harder, right? Than the
Yeah.
machine problem. Again, I just want you to think about this one a little bit. It took me even a little while to think about what they were asking here. All right, I mean, 5.45, you should be able to answer the questions given what was given. How about part A? What's the probability without medical intervention of having a boy?
This seemed extremely straightforward. 0.51.
Correct. Now, the second question, notice that they talk about a couple who wants a boy. That wasn't in the original, well, I actually do have it in the original thing here. It says researchers who used the process claim the couples who wanted a boy were successful 85% of the time, who wanted a boy.
Mm-hmm.
While couples who wanted a girl were successful 77% of the time. Now, if you look at my note, now, all right, so you said 0.51. How about the part B? What was your answer to that one?
I got 0.85.
Okay, and part C?
0.77.
Right. So they just repeated what was already in the problem, right? There's nothing different. You didn't really have to calculate anything, right?
Right.
Now, the question is, how do you set this up, right? How do you set it up? I mean, do you come up with two other variables that say want a boy or want a girl? Or look at the way I did it and see if it makes more sense. Let me stop sharing. And you tell me whether it makes sense or not, because nobody else in my household would know what I'm talking about. So, but you guys are smart, and I want to see what you feel about it. So, and let's just scroll down here. Now, here are the variables that I set up. Event B means having you have a boy. G is having a girl. And this is what I set up here. I said W is the process that they're using actually works. So the probabilities of B and G are clear, right? Probability of B is 0.51. The probability of G is 0.49. That's easy. What was not easy was setting up these probabilities, I mean, the notation for it. And the 0.85 says, and I think, and you tell me whether it makes sense, because in the body of the problem, it says couples who want a boy were successful 85% of the time. What to me that means is, what's the probability that the process work given that you have a boy? Doesn't that sort of say the same thing?
Yeah. Although all four of those probabilities that you list, 0.85, 0.77, 0.15, and 0.23, that there's also like another given, right? That they had the medical process done.
Right.
Right.
That's
okay.
true. That's true. But the 0.85 is not it's not the probability of having a boy given that the process was used.
Mm-hmm.
Obviously, that can't be that's to go from 0.51 all the way up to 0.85. That doesn't make much sense, right?
Right.
Right. But it's possible. It is possible. That's what they were asking for, right? The probability of B given that the process worked. Okay. What do you think? Now, do you think I set this up correctly, or do you think the 0.85 is the probability of B given W?
I think you set it up right.
Yeah, I think so too. Now, And then the second was the probability of the process work given that you have a girl is 0.77. All right. So I believe these probabilities have to do with whether the process worked or not, right? Not whether you had a boy or a girl, right?
Mhm.
Okay. And then, of course, these are the complements of each one of these, right? Which we didn't have to use in this problem.
Mhm.
Right. So A, B, and C is these three, this number, and that number there. All right, now let's go to 5.46. I'll stop sharing that. I don't know if you worked. Did you work on that too?
Yes.
And Han, did you work on that too?
Yeah, but I didn't get a result.
Yeah, it's a little harder. Now, this is where you might think maybe I didn't do it correctly, but let's see. Let's see if I did it correctly. So let's actually go back to the my results. And by the way, I would never ask a question like this on a test. All right, it's going to be simpler question, straightforward. But this is a good little exercise to just think things through. Now, in 5.46, assume a couple who wanted a girl was randomly placed into either the treatment group or the control group. In the treatment group, they're going to receive this process. In the control group, they're not going to receive the process, okay? So we know if it's randomly, if the treatment group and the control group, if everything's done randomly, the probability of being in the treatment group is 0.5. Everybody clear on that, right?
No,
You're not clear on that?
no.
If you have two groups, right?
Mhm.
If you have two groups, and you randomly assign somebody to one of the two groups, it's a 50-50 chance of being assigned.
Oh, so that is the prior probability,
Yes.
right?
Prior probability, yes. Stephen, that you agree with that?
Yes.
Okay. Now, this problem is actually asking you to recalculate the probability of being in the treatment group given that the process works. All right, which means the probability of T, which is being in the treatment group, given that the child is a girl. Okay. So I'm going to use Bayes' theorem because the probability of G being in the treatment group, all right, we're going to actually calculate that separately. Because this is what you need to calculate. The probability of T we're given, 0.5. Okay. And we already know in the denominator the probability of what T is, and also the probability of not being in T, which is the control group, would also be 0.5. This probability here, the probability of G given not being in the treatment group, okay, we have to figure out what that is. Okay. All right. Now, in the numerator, the probability of the girl being in the treatment group. Now, see if this makes sense to you. In the numerator, it's the probability that the process worked, right? The process worked. This thing here. The probability of W given G times the probability of G. Okay? Divided by the process worked and the process, plus the probability the process did not work. Okay, I noticed they got a boy instead of a girl.
Can I ask a question?
Yeah.
I feel like that's P G given W. Why is it G given T?
Well, let's look at it this way. I skipped a little step here. The probability of G given T is equal to the probability of the treatment group given G. Oh, wait a minute. Wait. The probability of the girl being in the treatment group. That's what this is here, right?
Mhm.
And again, let's see if this is right. See if you think this is right. If the girl's in the treatment group, then that's the same thing as saying that they're going to receive the process. Correct? If the
Could you
girl,
say that again?
yeah. What's the probability of the girl? If you know the child is in the treatment group, what's the probability that it's a girl, right? That's what this is here, I think.
Mhm.
Isn't that the same thing as saying, well, the numerator would be the probability that the girl is in the treatment room, that you have a girl and it's and the child is in the treatment group. Okay? And that's the same thing as saying, I don't know if I did, well, I don't know. I thought this through. I thought I got this correct.
My the answer that I came up with was I didn't set that. I plugged in like the most basic version of Bayes' theorem, which is just probability of A. Oh wait, I have to go back a couple of pages. Probability of. Sorry. Wow, I have to go back far. Where is it? Okay. Probability of A given B, and I set it up the same way that you did. Probability that they're in the treatment group given that they have a girl is the probability of A and B, which is the probability that they're in the treatment group, which is 0.5, times the probability of B, which is just 0.77. Yeah, because A. Yeah, I'm not sure. The answer I came up with is different. It's 0.7857.
You mean the final answer?
Yeah, not 0.487, but I
This answer is a lot closer to 0.5. It's got to be around 0.5. It can't be that much different than 0.5.
all right. Well, the place where I'm confused about the way you set it up is that part where you wrote probability of a girl given the treatment. To me, that's just I just thought that was 0.77 because it said that in.
But in the yeah. All right, let's go back. The way I'm just looking at the way I set it up. This is actually the probability. This is the probability that the process worked, given it's a girl. The way I set it up. It's not the same thing. One thing we could have done is calculate the probability, use Bayes' theorem, and calculate the probability that child is a girl given that the process worked, right? Which is what you were trying to plug in. We would need Bayes' theorem to actually, we would need to use this number here. We would need Bayes' theorem for this. I see where you're going with that, but I think that's what I ended up doing. Because here's the 0.77 right here.
Right.
Okay. I see exactly what you were doing, but I'm multiplying it by 0.49, which is the probability of having a girl.
Mm-hmm.
All right. The numerator is, the denominator is the same thing again, plus the probability that the process worked and you had a boy, right? What does that have to do with anything? That would be if Well, let me think about that. This is what it says, that the process didn't work and you had a boy instead. So let me think about it for a minute. What I'm really saying here, and see if it's equivalent. I'm saying that this here is the same thing as the probability of having a girl given that the process worked. Is it the same thing?
I'm not sure. I'm kind of confused myself.
Yeah, I mean, that's really what I'm saying here. I'm saying this probability, I'm saying, is the same thing as what you were saying before. Points, it's basically, that's what I'm trying to calculate there. All right. But what you're saying, it's 0.77. I think that's 0.77 is this probability here.
Mm-hmm. Mm-hmm.
Now, the only reason I'm showing you this problem is showing you how difficult this can be if the wording of the problem is confusing.
Right.
Bayes' theorem. Bayes' theorem problem has to be, and I struggle with this problem because of the wording. The wording is not really clear. All right. But I'm pretty sure, in my personal opinion, I'm pretty sure that the answer to the question in part B has to be close to 0.5. It can't be that much different than 0.5. All right, I don't think. Because the probability of having a girl is less than the probability of having a boy, right?
Mm-hmm.
So I would think the probability of being in the treatment group, given that the child is a girl, has to be a little bit less than 0.5. Just common sense tells me that. And when I got the answer of going through this whole rigmarole of 0.487, it seemed like that seemed to be consistent with my thinking. That's why I thought maybe the way I did it here was correct, even though it's kind of hard to understand what I did here. The probability that the child, if they, what exactly did they ask in this problem? What was the wording? The wording is the couple's newborn child is a girl, right? What is the probability that the couple was in the treatment group? So this is what they're asking. They're asking this the probability right here. Probability that if you have a girl, that they were in a treatment group as opposed to not being in the treatment group. Okay. Do you agree with the notation here?
Yeah.
And do you agree that with Bayes' theorem, it would be this?
Yeah.
Right. So the real question is, what is the probability of being a girl given that the couple is that couple's in the treatment group? What's the probability of being a girl? Now, I might have overthought this, right? I might have overthought this. Given this is an introductory text, I thought this was much harder than it is. This probability here, what's the probability that if the couple's in the treatment group, that it's a girl? Now that I'm thinking about it, what's the answer? It's 0.49. That being in the treatment group doesn't have anything to do with probability of being a boy or a girl, right? In general. This probability here, and now that I see it, I'll X out this part right in here. This should be 0.49. Shouldn't change the probability of being a girl, should it? Being a treatment group? Or does it?
I'm not sure. I mean, if
Well,
you're
they're
in
getting the
treatment-
process, right? If they're in the treatment group, they're getting the process. So is it 0.49 or is it not? They're getting the process for sure, because that's what the treatment group means, right?
right.
So they're getting, what this actually means is, what's the probability of G given of what? They're getting the treatment. They're actually getting the treatment, right? As opposed
Yeah.
not to getting the treatment.
I think that depends on if the couple wants a girl or a boy.
Yeah.
Okay. Let's see what it says here. Couple wants a girl. They're telling you the couple wants a girl. So it doesn't, so no, it has nothing to do with boy, or we know the couple wants a girl. Forget about the boys. Boys don't matter. Okay. So do you agree with me that the probability of, if the couple's in the treatment group, the probability that they get a girl, I might have done this correctly. Isn't that the same thing as saying that what I'm trying to find here is the probability that they're going to get the treatment, right? They're going to get the process. They're getting the process. So it can't be 0.49 then, because the process is going to alter that, right? So this cannot be 0.49. Probably the probability of being a girl, given that they're in the treatment group, cannot be 0.49, because that's the probability of being a girl, period. So what is that probability? Well, it's the same thing as the probability of getting a girl, given that the process worked, or that you've got the process, right? You agree with that?
Yes.
So this probability here, probability of a girl, given that they got the treatment, or they were in the treatment group, which means they got the process. Do you think I set this up correctly? That it's really this probability here? They want a girl. Think about it. They want a girl. They want that. That's what it says here. They want a girl. The couple wants a girl. So what's the probability of getting a girl, given they got the treatment? Must mean it's the probability of getting a girl, given that the process worked. Isn't that true? It's G slash, or whatever this bar here, W, because they want the girl.
Mhm.
And if they get the girl, that means the process worked. So what they're asking for, what this probability is saying is, it's the same thing as saying probability of G given W. And therefore, then you use Bayes' theorem right here to find this probability, which is 0.4653. Okay, 0.4653. Plug that into this formula up here, which is again Bayes' theorem again, and I get 0.4887 is the probability that, given that you have a girl, what's the probability that the couple was in a treatment group? And that's why I think that's where my reasoning came in here. Do you think this makes sense to you?
Yeah, I think, yeah, because they want a girl.
Yeah, they want a girl. So if they get a girl, that means the process worked.
Can I ask? Can I present the version that I did, and can you tell me where I may have gone wrong?
Assuming that I did it right. Maybe you did it right.
I don't, because my probability is weird.
Yeah.
So I looked up at page 153 at
Okay.
the general form of probability of event AI given that event B has occurred. So for that, I set it up as the probability of they were in the treatment group given that they had a girl. So A is treatment group and B is girl. So according to that, it says on all the way the equation on all the way on the right, that's probability of A, which is 0.5, as we established in part A, times probability of B given A. So that would be probability of girl given that you're in the treatment group, which is 0.77. And then that is just over the general probability of B, which is 0.49.
All right. Now, if we go with your version, then this is wrong up here. Because you put 0.77 as the probability of G given being in the treatment group.
Right. So yeah, probability of G given T.
So going back to here, if you are correct, then this is backwards.
Right.
You're saying this should be the probability of G given W.
I that's the way I interpreted it. Yes.
Mm-hmm. Okay. Okay.
But yeah, you're right. Intuitively, I feel like it should be closer to 0.5. Because the answer that you end up getting if you do it the way that I said is 0.7857, which means it's very likely that they had the treatment.
Right. So what I'm going to do, I might have, let me take a quick look. Give me 1 second. That's why I wanted you guys to try it out too. Because this is the type of problem that I think most people would just not do at all. But even I think professors will come up with different answers for this one. So what I want to do is go back to the, just give me a second. Oops, I can't get out of here. Sorry. Let's see. I'll go back to the book. And actually, I'm going to go to the instructor's site here. Here we go. And I believe if I go to chapter 5, I might be able to see the solutions for this problem. So let's see which solution works. Because your solution assumes everything is switched around, and my solution is the opposite. So I'm glad you came up with your solution because it shows 2 different ways of doing this.
Yeah.
So what I'm going to do is look up the answer to this. Just give me a second here.
Sure.
I believe I have access to this problem. All right, hold on a minute. Looks like a Word document. Yeah, here we go. And we'll take a look at the solution and see what we come up with. 5 and 4, 6. And I believe I have solutions to all of them. I didn't look at them, by the way, because I wanted you guys to try this problem also and see what you came up with. Give me a second here. I don't have you on anything here. It's like they use some sort of tree diagram here for the answer. Let me see what they come up with. And it seems like they came up with an answer that doesn't match either one of our answers. So let's take a look at it and see if what they did makes sense. Okay, so I think I'm good here. So let's go back to you guys here and share it. And where are we? Yes, this one here. All right. So notice what they used here. They did use that other way of writing a variable. They actually had two other variables. See, I had the variable which was the process worked, right? Which I think is a pretty interesting way of doing it. But they did it the way that I thought could be another way of doing it, which was create two other variables. One variable is they wanted a boy, a couple wanted a boy, and the other variables they wanted a girl. Okay. All right. So the way they did it was a probability of a boy is 0.51, which means the probability of a girl is 0.49. It says with this intervention, the probability of having a boy, given they wanted a boy, is 0.85. So that's the way they wrote it. All right, which makes sense.
Mm-hmm.
And then the probability of having a girl, given that they wanted a girl, is 0.77. Okay, so they actually created two other variables, wanting a boy and wanting a girl. All right. I don't really know. The only problem with this way they did it here was not wanting a boy must mean they wanted a girl, right? And not wanting a girl means they wanted a boy.
Mm-hmm.
So it's a little, I don't know, a little shaky the way they did it. No problem with this. We got the same answers no matter what our notation was. A, the same thing, right? The probability of treatment is 0.5. That was clear. Now, let's look at B. G is the child is a girl, and not G is the child is not a girl, which we'll assume means boy. All right, we're not going to go into anything more than that. All right, we're not talking about alien or something like that, something other creature other than a boy or girl. All right, now the posterior probability is what they're asking us to find is the probability of T given G. Probability that T given G. All right. And that's exactly the way we set it up too, right? That's exactly it. All right. They use this diagram here, but let's look at the formula that they use. The probability of T given G is the probability of T and G divided by the probability of G. Now they use Bayes' theorem down here, but they also thought, what's the probability that you have a treatment and the person's a girl? Well, they said that the probability of a girl is the probability that the girl and having a treatment plus the probability of a girl and being in the other group, right?
Mm-hmm.
So what's the probability of a girl? What do they do here? Wait a minute.
Oh, I see where I went wrong.
Hold on a minute. Hold on a minute. They're saying the probability of G is 0.63. That's not right. The probability of this is an unconditional probability here, right? The probability of having a girl, period, is 0.49.
That's what I thought too, but I guess they're saying that it's the probability of a girl given this whole situation, which means it could be that the treatment was not given, the treatment didn't work, or the treatment did work. So three possibilities. They didn't
Well,
get the treatment.
yeah, they're saying up here, the probability of a girl is equal to the sum of these two. I have no problem with that. But where do they come up with the 0.385 from? Where did that come from?
That is 0.5 times 0.77.
0.5 times 0.77. Okay. So it's the probability of having a girl, given that they wanted a girl, times the probability of what? They're in a treatment group.
Yes. But they could also get to a girl by not being in the treatment group and having a girl anyway.
Okay. I don't know if I agree with the solution. Because G is the child is a girl. The probability of a girl in general is 0.49. You can't get around that. You can't get around that. Now, if G is the child is a girl, and what else? They're in the study. And I don't know if that makes any sense. If you're defining girl, the child is a girl, and up here you're defining the child as a boy, then the probability of G has to be 0.49. So, okay, so here's the deal with this type of problem. It's very confusing.
Yeah.
Even their solution, I don't agree with this solution. I don't know if it's valid or not. Now let's look at the base thing here. Let's see if this is right. The base thing says, see, even in the denominator, they're saying the same thing, aren't they? It's 0.63, okay? Okay, they're saying the same thing. The denominator is 0.63. Again, I don't know if I agree with that. So, just hold on one second here. Yeah, I'd have to look through this again. I'm not totally sure this is correct, but the way they did it. So here's the moral of the story. I have to give you a problem if I give you Bayes' theorem. I have to give you one like the machine problem. Okay. This is probably the worst Bayes' theorem problem I've ever seen. Because I've seen Bayes' theorem problems in other books, and they're easy. They usually have a medical situation, right, with a new drug or something like that, and they're looking at the incidence of a disease, things like that. It's very easy to interpret it, but this problem here is not a good problem for Bayes. It's a difficult problem for Bayes, and I'm not totally sure whether this makes any sense or not. If you go through this book, ignore this problem when you study for Bayes. Look at the machine problem as a good example of it. And I'll try to find another one with medical. Steve, you would be interested in that, right? A medical one?
Yeah. I'm a self-diagnoser based on Google, so that's very reassuring to get those big theorem problems.
Yeah. All right. Anyway, this is not a good example because you and me and book, we're coming up with 3 different solutions. And to me, it doesn't make any sense to come up with 3, and all 3 of them could be right. One of those 3 could be right? So I have to go through this problem and think about it again, but I'm not going to waste your time with this anymore, this particular problem. What I'm saying to you is Bayes' theorem shouldn't be this complicated. It should be much easier question to answer than the way they did it here. But the real key to me is the probability of G. All right, the probability of the child being a girl. That's unconditional. There's no condition on it. Do you see it?
I think that that's true, but maybe in the system as they've set it up, there's the possibility of it being a girl, accounting for the situations where a couple gets the treatment.
Okay.
Yeah, when I worked the problem out myself, I did the same thing that you did. So my numerator is the same as theirs, but my denominator was 0.49 instead of the addition of those things.
Mm-hmm. And you would have a higher answer here. If this is 0.49 in the denominator, your answer would have been a bigger answer.
Yeah, it was 0.7857, which is why it didn't feel right to me.
Mm-hmm. Mm-hmm. Right. Okay. All right. So don't worry about this problem. I wanted to work with you, but this doesn't make any sense to do this problem at all. You guys are, by the way, are my guinea pigs for this course. This course is brand new. So I have to figure out what to teach in the future. And this problem here is off the table. Totally. All right. The machine problem is on the table. I think you understand the machine problem, right?
I think so.
Did we go over that? We went over that in class. Did you want to go over that one more time? The machine problem?
Is it 5.49?
Yes. Let's spend a second on that. I'm going to show you this problem. Let's go over it one more time. 5.49. And I'll show you how much easier Bayes can be understood with a well-written question. All right. So I'm serious. It's absolutely true. Is this it here? This is the, no, this is, sorry about that. Hold on a minute. I can get this thing out of the way. This is what I want. All right. Stop sharing. All right, let's go back here. All right, so let's go over this problem one more time, because I want you to feel comfortable in doing Bayes with a well-written question. So this is it right here, 5.49. And then you tell me whether this problem is so much better as a Bayes example. So we have three machines that are producing a product, okay? Doesn't matter what product, they're all producing the same product. Because this is some sort of a manufacturing process, they're going to check for defectives, defective product. And they found that over time, that machine A produces 3% of their product are defective, 5% of machine B's product are defective, and 10% of machine C are defective. So this is what I want you to do without looking at the notes again. I want you to try this again. Of the total output from these machines, 60% of the items are from machine A. So machine A produces 60% of them, 30% from machine B, and 10% of the output comes from machine C. And you select one item at random from the day's production, and you want to know the prior probability that the item came from machine C. Now, I think you can do this on your own, right? So if you're selecting an item at random from the output, what's the probability that it came from C? And what is your answer?
0.1.
0.1, right? So that's because 10% of the output comes from machine C. So that's straightforward. But now let's look at 2. If the inspection finds that the item is defective, all right, so we know now that you're not just selecting any item at random, you're selecting a defective item at random. What is the revised probability that the item came from machine C? Now, while you're working on this, I have to plug my computer in. It's running out of battery here. I don't want you to lose the connection. So give me a second, work on it, and I'll be right back. All right. So you both came up with an answer? What did you
Yes.
what did you come up with?
Han, you want to go or?
Han,
Can
you
go.
want? Hi. So what did you come up with, Han?
Oh, I got 0.233.
All right.
Yeah, I
Thanks,
got
Tim.
0.232558.
Okay.
So it rounds to 0.2233.
Good, good. So you're both correct. And then the solution, of course, let's just look at it. Do you agree this is a much better problem for Bayes? Very easy to understand,
Yeah, it's certainly more clear cut.
more clear cut. This is the way Bayes should be. It should be clear cut. It should not be confusing. So let's just take a quick look at it, and then we'll just take a look at one more thing before we sign out for tonight. All right, so these are the probabilities of A, B, and C, of course, and then we have our probability that it's defective given that it's machine A, machine B, and machine C. Right? Would you agree that those are the correct notation for those probabilities? And what we're being asked to find in B is the probability that it's if we select a item and it's defective, what's the probability that it came from machine C? That's the probability of C given D. All right. And so that's equal to the probability of C and D, which is also equal to the probability of D given C times the probability of C. All right. Denominator, of course, is the probability of D. So, correct? Yeah. So the numerator, we know all of this in here, right? All of it is given. Notice the denominator says that the probability that it's defective is equal to the probability it's defective and came from C, or the probability it's defective and came from A, or the probability it's defective and came from B. And then you create these three terms here. All right. One of which is the one in the numerator. Right?
Mm-hmm.
So when you fill in all the numbers from up here, you get 0.233. Is that the way you guys did it?
Yep, exactly the way.
Yeah. And as you can see, if you wanted to find any of the other probabilities, since the denominator is going to stay the same. So if you wanted to find the probability that machine A was that the defective came from machine A, then you just replace the numerator with this term. Or from machine B, the numerator is replaced with this term. The denominator stays the same. So this is a classic Bayes theorem problem. Simple, straightforward. For most students, difficult, right? This is difficult for most students, but you guys, compared to that last one, this is a piece of cake, isn't it? And this is the way it should be. It should be a piece of cake if you know how to work with Bayes. All right. And by the way, Steve, you mentioned that formula in the book. That's what the denominator is right here.
Right.
The denominator considers every case for defect. The probability of D is equal to all three of these because this is the only three cases that we could have a defective item because there's only 3 machines. We had 5 machines, we'd have 5 terms down there. 10 machines, 10 terms. See what I'm saying? So that's what that sum is. It's basically saying all those possibilities, all of them. This is, by the way, this denominator is called the law of total probability. The law of total probability, which says the probability of D is equal to the sum of the probabilities that where D can occur. And they can occur with machine C, with machine A, and with machine B. All right? And there's no other possibilities. And they're mutually exclusive. They're mutually exclusive too, right? This probability is mutually exclusive from this one, and it's mutually exclusive from this one. It's either going to be from, the defective is either going to come from machine A, from machine B, or from machine C. It can't come from 2 machines or 3 machines. It has to come only from one of them at a time. All right. So this, again, I wanted to go over with you because you could see how much easier this is. And this is a classic Bayes problem, and it should be like this. This should be a problem like this. It should not be more difficult than this. All right. Ever should never be more complicated than this. All right. And then finally, the last thing I wanted to go over, unless we already went over it, I think we already went over it, which is the permutations and combinations. So I believe we covered everything in chapter 5. All right. We've covered chapter 5. Do you feel, both of you, do you feel that this was enough problems for you to know how to do in this chapter, or do you want more homework? You want me to give you more homework? You feel like you need more practice in any of this?
Either way is fine with me.
Han, you feel like you need a little more practice?
I mean, either way.
All right.
Just
Maybe.
Honestly, I feel like I thought I prepared well for test 1, and I didn't have enough time to finish. So I feel like no matter how many homework I did, I will not have enough time for test.
Right. And you watched, let me ask you something. You watched the video?
Yeah, I did.
And you prepared? You went over all the material?
Yeah.
And you still found it difficult to finish? And Steve, you finished it, right?
Yes,
How much time was left when you finished it? Did you barely finish it, or did you have some?
I had 3 minutes left when I finished.
3 minutes. So it was tight. It was a tight fit. Yeah.
Yes.
And Han, how many problems did you not finish?
The last question, because I feel like I can finish it with my calculator. Then when I go to the next question, I feel like, oh, I need to use the Minitab. Then
Yeah. Now, the last question was meant to be mostly extra credit. So if you finished everything up to that last one, that's fine, because you had 96 points right there if you got them all right. If you got the first 16 questions right, you would have got a 96, which is a very, very good score. So I meant for that last question to be extra credit if you happen to get through the other 16. I just threw it in there to give you some extra points, everybody some extra points. Remember, an 86 is an A in this course. All right. So I'm giving people extra credit for the tests. So 86 and 74 is a B, 62 is a C, and 50 is a D. All right. So the quizzes are also part of your grade, and the homework, and not the homework, the projects are part of your grade. And once I get through all the grading, I'll assure you that you will do much better. You've done probably very well in the projects. The quizzes, well, it depends, but probably get better than the test, maybe. So and so the tests are going to be, they're not supposed to be, everybody gets 110. It's not going to happen that way. All right. Somebody could get 110. Somebody, as we move forward, it's going to be more difficult to get over 100 on the test. That's why I made the A 86, because this is not easy. This course, even if it's introductory, I don't think anybody's ever gone through an introductory statistics course and say, "Boy, that was a piece of cake. I want more." It's just nobody says that. All right. So don't feel bad if you didn't get the score that you wanted. If you didn't have enough time, well, that makes sense, because again, I made that last part extra credit. So if you got through the first 16 questions, that's good. You had enough time to get through it. That 17th question, pretty much almost all of it was extra credit. All right. That's why I threw it in there. I was debating whether I should, and then I said, well, in case somebody does get through the 16 and still has maybe 5 minutes left, they may have enough time to work on the extra credit. And I decided, all right, I'm going to throw something extra credit in there and see how they do. All right. So now I would be worried if you only got half the test done. You know, then I'd be worried. Then I overdid it. But if you got the 16 done, then that was my expectation. You could get that done in 75 minutes. All right. Anything else, or you guys are good?
Fine.
You're fine. All right. So what we're going to do next week, now I might do a couple more. If I'm going to look through the problems in the book, see if there's any that you could do as a graded assignment, which would help bring your scores up. So I might do that just for the. All right, good, Han. So you actually prefer having some homework then? All right, if it's graded, right? All right. So next week we're going to work on chapter 6. And this is the beginning of what's called probability distribution. So we're going to spend probably maybe 3 sessions on that, maybe 4. And then chapter 7 would be starting on the normal distribution. So that's it for now. Anything else? So we end up a little bit longer this time, but that's okay. You guys helped me out a little bit. I helped you out. So yeah, I'll do a little bit of homework. I'll get that together for you. So next Tuesday, it'll be due. All right. It'll be a short assignment, nothing, maybe 1 question from each section or something like that. Okay. So let me stop sharing. If you don't have anything else, I'll let you guys go. Maybe I'll stop the recording.